Hi. So before we start some a main thing first. Homework 4 has been put on the blackboard, so you will be due on next Friday. Okay, not this, next. So you have 2 weeks to go, and after this homework, there will be another homework for hypothesis testing once we finish, and then there will be another one. That will be that's the end. So in total, that will be yes. Yes, we will. Absolutely. So the last week, I mean, at least the last class, we'll cover. We'll go over the past year papers. If we have 2 classes left, we will cover 2 years. If only 1 class, we'll cover 1 year. I'll put the question there later. But I think we will have. We have enough time, so don't worry. I mean, this we'll finish it like next week, and then we will have a NOV, and NOV will be quick, 1 or 2 1 week, and then the rest will be regression. So, but everything, I mean, the reason why we can go fast for the subsequent is because everything is based on what we have learned. So what we learned in this class is hypothesis testing, and later you will see ANOVA, which is the topic after, which is directly related to here. So so basically it's just we learned this, and basically most of the knowledge you learn is will be enough for the rest of the course. So hypothesis testing. So to remind you what is it, and it's good to have to know the big picture very quickly, right? I just keep drawing the same diagram again. Is with the population, okay? And we want to know some parameter of interest like mu, sigma square, and also say pi, right? If you consider the case of binary data, right? And we said to look at this, and then what we do is do sampling, right? And do sampling. And this is sampling. And full sampling, all right? What we are trying to see is we try to use some estimation method, right? Some estimation method, right? Which involve 2 things, right? Point estimation and interval estimation, right? And point estimation are x bar, s square, and p, right? And that is how we do that. And interval estimation is like x bar plus minus m, and also p plus minus m as well, right? And we learn m would be like if you know sigma square, m would be just z over 2 sigma over n, right? Sigma over n, right? And if you have no idea, right? If you have cross, then it will be t n minus 1 alpha over 2 s over root n, right? And for this case, you don't need to know it, right? It's just p times 1 minus p over n to the square root, right? So that is how you have learned the last topic, right? And what we talked about last class, we hint is the and also talk about that is called hypothesis testing, right? So hypothesis testing is the case where you try to estimate these 2, okay, or actually these 3 at the end. You will see today we put t-test is try to see if we have a hypothesis h null, right? H null is mu equal to a certain number a, and say mu not equal to a, mu bigger than a, or mu less than a, right? And we try to see if this is true, right? And how do we do that is it's very similar to the interval estimation, right, is see whether the interval you construct contain the parameter you have, right? Or in the other words, is under this hypothesis, right? If this is true, right, this will be centered on A, right? And we would say, right, your data does not support the hypothesis, the null hypothesis mu with A, if the data you found is far away, right? If either is here or either is here, right? And this will constitute a counter evidence for the null hypothesis, right? If it is not equal to, then these two are considered as an evidence against the null. If this is your alternative, then only this will be considered as the evidence against the null. If this, only this guy, right? So then we say how far away from this, right? X bar is here, your data, right? How far away is considered as big enough, right? Is look at the not look at the distance, but look at the in terms of probability, right? How big or how small is this, right? And usually in the case, you don't really look at this, right? Instead, you transform this to the Z space, right? You look at your 0, right? And you look at your data, you transform it to the Z, right? Which is X bar minus A over sigma over N, right? And you look at this particular area, right? And this is called the p-value method, right? If the area of the purple is very small, then say the alpha, which is predetermined by you, right? Usually it's 5%, 10% or 1%. If this is too small, then you would reject, right? And alternatively, you can compare it to, say, Z alpha or CO alpha 2, which are called the critical values. If your data, your test statistics shows your test statistic is more extreme than these values, then you would reject, okay? So these are the things we covered last time, okay? So what we are doing today is actually we would drop the assumption that we know sigma square. And apparently, it will actually follow the analog we have. When we don't know, we just T, okay? So basically, everything is the same, except that now we don't have Z, we have Tn minus 1, okay? So that is the difference between the two, right? The main thing is like when we have, we don't know sigma, and we have used the T bell rather than the Z bell, right? It's kind of like, you can imagine just like the what we call the small sample adjustment, right? When N is small, then you have to use T, right? Because when look at the case when N is super large, then we know T of N is same as the Z. Okay, so that is one idea behind. Okay, is that okay? I mean, we'll go to the detail. Okay, if any question. Is that a question? Because this is just overview of what we have been doing. I mean, you can see we just view things one by one. And okay, no question. Then I'll go to the this guy. Okay, just to remind you, X null is the null hypothesis. X1 is alternative, and X null is the X or X0, X naught is the things that is given, and X1 is the idea we try to find the evidence to see if they hold or not, okay? I'm not going to go to the example again because I think that would be, we're doing it by T, so everything is the same. So I just directly go to the idea, okay? So here we can see you don't know sigma square. That means that you have to use S square, okay? And in that case, by T, right? Do note that here we have to make sure that the very important assumption is we have normality here, okay? And that is different from the case before. The main reason is you can rely on central limit theorem if you know sigma square, right? If you know sigma square, you can do it by, even though without this, you can use central limit theorem, right? But now we are unable to do that because we don't know that. We have to use S square, okay, to estimate that. Then we cannot use central limit theorem, but we have to rely on normality, okay? So that is the bell shape. Is very important. You have to assume the underlying population is bell, okay? Which you are unable to know what's going on, okay? You have to based on you think this is right, and then you can try to check if this is right, okay? You can never verify, right? But you can try to look at the data and plot a histogram or and see if it looks like a bell or not, right? Because under normality, your sample you collect also should follow bell, right? So so that is something that you can really check. And it is beyond our class to talk about the case. It is not, okay, but that is what we are trying to do. And do note that it's n-1, okay? So you probably ask why n-1. There's definition, and the definition of how we define t and chi-square. Okay, so that's how you check your table. Okay, so let's see the example. I think that would be much more straightforward. Okay, so again we will do 3 types of tests: right tail, left tail, and both tails. Okay, and this is the last time we do 3 times. Okay, afterward we will just do 2 tail tests. Okay, here is the last time we do the test for 3 times. Okay, afterward I will just do 2 tail tests for the rest. Okay, you will know how to do the 1 tail. Okay, so the question again is we have, this is our step 1, right? We have to write down our, this is our step 1, right? We write down our hypothesis. Okay, and step 2 we construct the test statistics. Okay, this is step 2. All right, step 2. Okay, and step 3 will be make our decision. All right, so that will be the 3 single step. Okay, and you can easily see that almost the same, right? Only thing it changes just here, right? If I have sigma, I have z here, then everything will mean the same. Okay, so the only difference is I replace the s by sigma by s and t by z by t n minus 1. The reason is being this is the distribution of the test statistics, right? Now I guess I should talk about the example. Okay, suppose a population follow normal. So remember, the normality is important. Okay, the normality is important. And we consider a random sample with sample size 16, sample mean is 5, and S is 2. Okay, so make sure that the only assumption we make is assume the population is normal. Okay, so that's the only thing we are making. Everything is come from the sample. And we are testing the hypothesis mu equal to 4. Okay, so do remind yourself why we have mu equal to 4 is something that we want to test. Okay, it's given by your boss or given by standard or given by a situation you want to see the data supporting equal to 4 or not. Okay, so that is the idea. Okay, and the main thing is if you have this normal plus this guy together, which imply the following, right? X bar will be a bell curve. 4 is here. Okay, and this bell curve is not the, if you know the sigma square, if I tell sigma square, then this will be a standard bell curve, is that bell is a normal bell curve. But you don't know, instead use S. Okay, this, okay, is not a the usual bell curve. Okay, it will be, it has to go to the T. n minus 1. Okay, so that is the main difference is this guy. Okay, is this Tn minus 1 is the difference between what we have learned last week. Okay, so here the thing is x bar is 5, so it's here. Okay, so the question again is this distance big enough, right? Is this distance big enough? Okay, to say that 5 violates 4, right? Because I want to see if this is 4. We want to see the data support is 4, and we will consider not 4 if it's sufficiently big, right? Because that's how I write the alternative. Okay, and that means that I want to see if this is big enough, right? Is it small enough? If this is so small, then I would say 4 is very unlikely, right? It's far away. Okay, and to evaluate this guy, we have to convert it to a t, right? So that has been doing same a bell curve, but it's a fatter bell curve, right? Something like this. Okay, and go down, right? So what is this guy in this same idea? It's like here. Okay, the test statistic is come from here. Okay, you take 5 minus 4, right? 4 come from here, right? It's from here. Okay, and 2 come from the S, right? You see, and a square root of n, right? So that tells you this is 2. Okay, and as I said, there are 2 ways to do it. Either you can do it looking at the area directly, or you compare the critical value. Okay, so first thing, we just do the direct method, right? Just come look at this one. Okay, look at this area. Okay, and what's this area? Okay, this area is, look, Excel will give you the left area. Okay, so that's why you have to take 1 minus. Okay, and this, the answer is t dot this. Okay, and you put 2. Okay, and you have to put the degree of freedom, which is 16, so is 15. Okay, and then put true. Okay, so that would be the answer. Okay, so let me look it up in Excel. So what I'm doing is I will do this. Okay, 1 minus t dot this. Okay, 2, 15, and true. Okay, so, and you can see the answer is like 0.03 is less than 5%. Okay, so if you put the significance level is 5%, so you would reject it. If it's 10%, you also reject it. But if you use 1%, you don't. Okay, so if you use 10% and 5%, you will say my result is not supporting the our data doesn't support our hypothesis. If it is 10, if you use 1%, then you really can't reject. Is that clear what we are doing? Okay, is it sufficient? The area is sufficiently small, and turn out this area is 3%. Okay, so this is as we said, this is a direct method, and this method, p-value method, is very convenient when you have calculator, right? And because calculator, you can easily get the answer, right? But in terms of exam or when you don't have calculator, when you have table, then you really can't use this method, right? Instead, you will use the critical value method, right? Just the way to proceed is instead of looking at this, look at T15, right? Also a bell curve, right? At 0, okay? You want to, instead of looking at this, you go back to ask yourself, if here I want a 5%, okay, or which means 0.05, okay, what is this number here? Okay, what is T15? 0.05. What is this guy? Okay, what is this guy here? And if this guy, we call the critical value, is less than the T, right? Say if your T is here, then you don't reject, right? If it's here, then you reject, right? Because if just test statistics 2, right, is bigger than the critical value, then area must be less than 5, right? Because the more right you go, the area gets smaller, right? So you want to calculate this area, okay? How can you do that? Remember, Excel will give you the very left area, okay? So that means that this area, right, is 95%, right? So if you plug in Excel, it will be T inward 0.95, okay, and 15, okay? So that is how you get this number, and turn out this number is 1.75. So it's this case, okay? Sorry, it's this case, okay? So the critical value is larger than your test statistics, right? So that means that on the right-hand side of test statistics, right, will be much smaller than 5%, okay? So then you also reject, okay? So let me show you this T inward 95 here, okay? T dot inward 0.95, 15, okay? So this is 1.75, okay? So you can easily see that you can easily see this T inward 15, right? 95, 15 is telling you that you'd also reject this now, okay? So you can see the p-value is a little bit more convenient because you can easily change your mind and use different significance level, right? But use the t-table method, use the critical value method, which only tells you particular value, right? But if your table, then it's more convenient, right? You don't need to calculate every time. Okay. Is that okay? Is that clear what we are doing? Okay. Don't worry, we'll do again for the left-hand side and two-sided one. Okay. Then you should be able to see what we are doing. Okay. This is the last time we do right tail and the left tail, and then I'll just do two tail from the onward. Okay, because it's too boring to keep doing the same thing. Okay. Now we know we reject this. Okay. So now the question is same. If left-hand side, everything is analogous on the left-hand side. Okay. So I think I can skip this slide and directly go to the example. Okay. And we start with a normal distribution. We have a sample size 16, sample mean is 3, sample centimeter 2. Okay. And the data set mu is 4. Okay. So do note that you're careful, mu is less than 4. Okay. So what we have is the following, right? We have an X bar here. Okay. And if we have sigma square, okay, if we know this, okay, then it's a bell. right? There's no problem. And according to the node, this is 4 here, okay? So the question is what we have. The data tells us it's 3, so it's here, okay? And what we are trying to do is we're trying to see if this area is so small, okay? If it's small, then it represents this distance is large, okay? So that's the idea, okay? And to calculate this area, right? The way to proceed is because we actually don't know this guy, okay? So this cannot be calculated, right, directly. So what you have to do is to convert this to what we call the t n minus 1, okay? In this case, it's just t15, okay? T15 here, right? And this becomes 0, okay? And once we draw this guy here, okay, and turn out this 3, okay, it's going to be -2, okay? How do you get that? It's coming from this one, right? But this is how you get this subtract 4 and the same operation, but you just replace sigma by s, right? So just minus this and over this, right? And turn out in you transform it, this is the area, the same area, right? So that's why it's okay to look at T15 instead of the bell. Is that clear what we are doing? Okay, so then look at this area. If the purple area less than 5%, then we're done. Okay, so again, how can we find this guy, this area? Okay, so just very simple, because Excel directly gives you the answer because this is the left-hand side. So just T dist, okay, -2, 15, true. Okay, so that would directly give the answer 3%. Okay, so I guess it's good to show you again Excel how we get the 3% here. Okay, it's the T dist -2, 15, true. Okay, so that's how I get it. Okay, so that's how I get the 3%. Okay, so exactly this guy, and you should know how to do it. Okay, is that okay? How I get this number? Okay, so this is already written here, so I go back to the slide and then stop a bit. Okay, so this turned out to be less than 5%, so you would say the data were not supporting our hypothesis of equal to 4 with 5% surveillance level, right? If you use 10%, you also reject, right? But you use 1%, you don't, okay? It depends on how large the type of error you want to endure, okay? So that is very important. The next thing is look at the critical value, okay? And as I said before, same as what we have done before, so we just, to do it, we just look at the area directly, T15. I hope you can keep the voice down a little bit for those who are talking among themselves. So this is 0 here, okay? And you want to find the alpha. This is very small, okay? 1 alpha. And then later you compare it to -2, right? See, -2 is in this area or in this area, right? So first we find T15 alpha first, okay? So how can we do that? How can we figure out this? Sorry, I should use that color, right? We want to find this T15 alpha, okay? So this is just because the area is given to you, right? Alpha is like 5%, as standard we are doing. So just T inward 0.05, 15, okay? Because the area given is left, okay? So this is the answer, and then turn out to be 1.75, actually negative 1.75, right? You look at it, it's negative. Actually be negative because this is negative here, right? Should be negative 1.7. Okay, and that means that 2 is actually here. Okay, 2 is actually here. Okay, so negative 2 is actually here. Okay, it's actually in this one. Okay, that means that the area to the left of the 2, negative 2, will be smaller than 5, right? So this area is small enough, then you also reject. Is that clear what we're doing? Okay, so this area is less than 5%. Okay, so I think I don't need to write this, right? I don't need to show you in Excel. I think it's clear. Is that okay? I hope it's you know how to operate. This is the only last time you do the left tail and right tail. Okay, from now on I just do two tail. Okay, no more both tail because I think the same. Okay, just to bear in mind the p-value will be a little bit different. Okay, and as I will do one more two tail, then you will see. Okay, is that okay? Is there a question? Is there a question before we proceed? Is that okay? So as I said, we'll repeat this several times. I would hope that it would not be an issue for you. So, okay. So let's do the two-tail test. Okay. The only thing that you have to be to remind yourself is the p-value is 2 times of the one-tail one. The reason is being that you put alpha on both sides. So actually compare alpha over 2, right? The idea is if a t here, right? The main thing is you put 1 minus alpha in the center, so the both side is alpha over 2. Okay, so we basically compare the value you have, suppose here, you compare this value with alpha over 2. So that's why you multiply the value by 2 compared to alpha. Okay, so there's no particular reason why they multiply by 2, but because you want to always compare alpha, right? So that's why that's how they do it. Okay, it's by convention. Because you really don't know which side appear before you do the sample, right? So that's why you have to include both sides. So that's the main reason, because you are saying alternative is not equal to, right? That means that you don't really know which side you're doing, right? So it can be both sides, right? Depends on what the data tells you. Okay. So let's actually head to the example because it's very mechanical. Okay. And actually the same question, except we have the only difference from previous example is only changed from less than or equal to, so less than or more than, to not equal to. Okay. So the main thing we have is, this is the idea, right? We have things under normal distribution, right? So that means that this X bar will be a normal bell curve. Okay. If we know sigma, okay. So if I know this is the bell curve. Okay. This is the variance of this, and this according to the null 4 is here. Okay. And again, look, but I don't know where it is. Is it here or is it here? I don't know. Okay. This is the two-sided one, right? It can be violate. I don't know which side to violate. And turn out the data is 3. Okay. The question is this area, okay, greater than or smaller than alpha over 2? Okay. It's not alpha. Okay, because two-sided. Okay, because you would put, if either here or here, you'll reject, right? So that's why you would be also worried about that, right? So that's why you just look at alpha over 2. Okay. And the thing is, we don't know this sigma square, right? So that's why what we are trying to do is convert this to the t, right? So t n-1. Okay, in this case we have t15, right? Because n is 16. Okay, and the conversion, right, is just right. How you convert this, right? It's just by this formula, right? You minus the mean over the standard error, right? So 3 actually convert to -2, right? And you want to, again, the same as what we have said, we want to compare this area to alpha over 2. Okay, is it bigger than or less than? If less than, you reject, right? So, and this area, I think we know where how to do it, right? It's just the t dot this, right? -2, 15, true. Okay, and this is this area, but to calculate p-value, multiply by 2. Okay, is that clear? And that gives you 5 like 0.6%. Okay, so you can't reject. Okay, you can't reject. So maybe I show you the Excel again, because seems like it's good to t dot this. Okay, -2, 15, true. Okay, so here, I mean, as you can see, this number is bigger than 5%. Okay, so you can still reject it by 10% if this is what you want, but if you use 5%, actually you can't. Okay, so you can easily see that a one-sided test and two-sided test will give different result, right? Because you know exactly where it is, right? Then it's different. Okay, you know which side you want to collect evidence. It's different from both sides. Okay, because you multiply by 2, right? So that means if you two side, actually a little bit you require much stricter evidence, right? And that's why you fail to reject, right? So that means that if the interpretation will be the data is still consistent with equal to 4, right? So that is what we are saying. And the other way around is look at the critical value, okay, which is 2. Okay, so how can we calculate that, right? Is here, right? T15, right? And 0 is here. What we try to do is look at this. Okay, remember, look at both sides, right? Both sides is alpha over 2. Okay, so and this value, right, will be just t inward because alpha we use 95, right? 0.95 here. Both sides will be, this is 0.025. Okay, 15. Okay, if you look at this guy, okay, will be t inward 0.975, 15. Okay, right. So that would be the two values, but you know they are symmetric about 0, right? So this will be 2.1314, and this will be -2.1314. Okay, so these are two critical values. Okay, so your -2 is actually here. Okay, -2 is here. Okay, is not more extreme than the critical value, so you can't reject. Okay, is there any question? So I showed Excel because it looks like you're not very happy with Excel. T dot inverse, okay, 0.025, which is the left critical value. If you put T dot inverse 0.975, okay, will be the right critical value. So either you have the left hand side is 0.25, right? 0.025. The right hand side is 0.975, right? Because the middle is 95, right? So both sides 5%. Okay. So that is what we have. Is there any question? So in this particular case, I think we haven't done so far is actually we failed to reject, right? In this case is, okay, the data doesn't against what we have originally. Okay. Is that clear what we have been doing? Is that okay? And although we have 2 minutes before a break, but let's have a break earlier. And then after break, we will talk about a binary data, a special case. And then we are done with the 1 sample test. Okay, then we'll go to 2 sample tests. Okay, so I'm pretty sure we should be able to finish every material for the semester. So don't worry. Okay, so I go around to send a question. So let's resume at 1:30 as usual. I go around to see if there's any question. Even more extreme, even this extreme case of how likely to offer this more extreme when already both sides. Random or even the boundary actually an example. The same thing. Yeah, it's not I guess someone asked if how can we do the T table. So quickly go to T table. So how can you find this guy? Okay, T15.05. So it is not difficult. So let me try to look at any T table on the web. Okay, and as I said, you can actually construct by yourself, right? Because you know how to do Excel, right? But if you don't like to construct, you can just pick up one. Okay, and I just randomly pick this one, I guess, because this one I think I use it the dummy one. Okay, so this is just maybe I open it in a new tab. Okay, here, right? This one is good because this one actually gives you the right tail already. So I just go to this column, which row is the degree of freedom, P is the right tail. So here I have, I don't know, I have two tail or one tail. I have two tail, so 5% is 0.025. So that means that I'm looking at this particular column. So it's 1, 2, 3, 4, 5, the fifth column. Okay, so the fifth column. Then I'm looking at degree of freedom is 15, right? So just this guy, okay, 2.13. Can you see that? I mean, I just circled that 1 hour. Okay, so this one. Is that clear how we find it? Okay. So of course, maybe I give another example how you can do another t-table. I mean, in case you would. So suppose I pick this one, the same idea here. So this t-table actually has a good thing is the 2 tail and 1 tail. So I guess it's yeah, this one, right? So it's this guy. Because 2 tail 5%, okay, same as 1 tail 0.25. So this is the guy, and you go down to check 15, okay, it's here, right? 2.131, okay. So in the worst case in your exam, right? If you really don't find it, you can just write the Excel formula, right? And then you will just at least have you may miss the last part, but you still answer most of the question, so shouldn't be deduct a lot of marks from that. But in the worst case, but I recommend you bring your own t-table, okay? Because you can bring as many as you want, okay? You can bring multiple versions of t-table if you want. I mean, there's no limit of number of pages, okay? Just make sure you have your own one. The reason why I don't print it for you because everyone have their own taste, right? Because so that's why, in order to reduce waste, okay? So now we have the other one that is actually you would be expecting is what about binary data, right? Binary data. The binary data has a very nice feature because if under H now, okay, we make assumption about the population proportion, right? A, that means that the variance is also be pinned down, right? Because you make the assumption on the mean, you also make the assumption on the variance, okay? And also someone asked me in the during the break, sometime how do you call this guy? This guy is actually called standard error, right? But I seldom use it in our class because it's just this is often used outside in many textbook, but I seldom use it. But standard error simply mean the standard deviation of the sample mean. Okay, just to let you know. Okay. Anyway, so I guess this is clear. Everything is same because law of large number. Okay. So do note that this is a good thing about binary data is you don't have to talk about t. Okay, you don't need to talk about t because once you assume this null hypothesis, you know the variance. Okay, so there's no t you need. Okay, so that's also a good thing about the proportion is you don't need to talk about t. Always the always is z. Okay, so I'm not going to talk about the both sides. Okay, I'm not going to talk about left and right. I only talk about the both sides. Okay, because it's so straightforward. I think it's very boring to keep bothering with both sides again. So I just do two-sided one. Okay, so exactly the same. Okay, the only difference is there's no difference except you just apply directly the formula. Okay, so let's go to the example and then we see how we proceed. Okay, so the question now is we don't need to assume anything normal. So it's very simple. Just basically no assumption needed. Okay, I'll tell you assumption we have to do. Okay, first is you look at the data. You have 50. Okay, and you have p is 0.5. Okay, so what's hypothesis here? Is equal to 0.4 and not equal to 0.4. It's two-sided one. Okay, and what is needed for you to make this work is to make sure that n pi is bigger than 5 and 1 minus pi bigger than 5. Okay, so how can you make sure that? Because you know the pi already, right? So as long as you collect the data that is more than 5, then you're done. Okay, so that means if you do that, n pi multiplied by 5, then the central limit theorem holds, right? So we can use this formula, right? So we can have this p sample proportion will be a normal. Okay. This normality comes from here, okay? Remember, come from if you have this will be a good approximation. So as long as n pi and n times 1 minus pi is more than 5, right? Then you don't have problem, okay? And here we have by the null hypothesis, which is 0.4 here, okay? So what we figure out is the data tell us this is actually 0.5, so it's here. Okay. So what we want to see is this difference large enough? Okay. And how do we do that? Is see whether this guy is big or small, right? You compare it with alpha, right? Because alpha is the tolerance level of sampling error, okay? Because you assume H now is true. It will also end up in this area, even if it's true, right? Because data you collect is also end up here, right? So how much we say the sampling error is small enough to reflect that it's actually not 0.4. Is that clear what we are doing? Okay? Is that clear why we have compared to alpha, right? It's because even if X now is true, it will still end up in 0.5 or more, but we would only allow our alpha, right? It's the tolerance level, right? Okay. And this area is called p-value, right? It's the p-value defined here is how large is this. But do note that we have two-sided, okay? So instead compare alpha is alpha over 2, because we do it before we do the data collection, right? So we both side alpha over 2. We just try to compare, is it more than or less than alpha over 2? Okay. So let's go for it and see. Okay. So remember, we transform this to the Z, okay, to make everything nice, okay. Because this is normal already, right? So, but we just transform it to here, right? 0.4 becomes 0, right? And what is this 0.5? Okay. How can you transform this? Is this formula here? Okay. This number 1.44 is we call test statistics. Okay. And how do you do that? Is just minus this over this guy. I think this is the we do the interval estimate. It's the same thing, right? It's the bottom guy there. Okay. Is that okay for this one? Because this is just 0.4, 1 minus 0.4 over 50. Is that clear what we're doing? Is that okay? So what we end up is we want to look at this area. Okay. Is this area big or small? Okay. And either you compare this area to alpha, or you multiply this area times 2, right? And compare to alpha. Is that clear what we are doing? Okay, so the same thing here, right? So since this is normal, right? That's why this just means because this area is 1 minus the left-hand side, so it's 1 minus norm S this 1.44 true. Okay, and it's not n, right? Because it's multiplied by 2, so we just have to do this 2 times. So this will be the Excel input. Okay, because you have to calculate the p, you multiply by 2, right? You compare it to the p-value. Is that okay? So let me go to the Excel and tell you that this is actually 14%. Okay, so actually do that 2 times 1 minus norm S this 1.44 true. Okay, close bracket, close bracket. So that gives us okay. The reason you multiply by 2 because you compare it, it's two-sided test, you multiply by 2, you compare with alpha. Okay. And the reason why there's 1 minus because Excel only gives you the area to the left. Okay. So that is the reason. Is that clear? Is that clear? So from this, you can't really reject because it's neither less than 10%, neither less than 5 or 1. Okay. And probably I will remind you what is this, why this p-value, right? P-value is the probability that you would actually kind of observing this outcome, even though this is true, right? More extreme than this value, right? The next thing is the critical value method, right? And that is likely what you would do in your exam, right? Is to how to calculate this, right? The same idea here. This is a Z, right? We'll be looking at 0 here, right? We are looking at 95% in the middle. Okay, so that means that this is 2.5%, 0.025. Maybe other color to make it. So here is 0.025, right? And here is 0.025. Right? Add up is 1. And this value will be just Z, negative Z, 0.025, right? This is Z, 0.97, sorry, 0.025, okay? And this is just the norm dot S dot inverse, right? 0.975, right? And the other one will be just norm dot S dot inverse 0.025, okay? And this is just negative 1.96. This is 1.96. Okay. Is that clear? I hope that is clear. And this is 1.96, and look at your data is 1.44 here. Okay, you're here. Okay, 1.44. So your critical, your test statistic is not more extreme than the critical value, okay, which is 1.96 or negative 1.96. Is then you really can't reject it. Is that clear? Is that okay? So actually, if you don't use the Excel or whatever, the rule of thumb is like 2, right? As you can see, right? Look at the test statistic. Is it more than 2 or less than 2? Right? Of course. Or more than or less than is it more than 2 or less than negative 2? Right? That would be the criteria, right? Of course, depends on whether you do two-sided or one-sided, but apparently 2 will be the thing that usually you would be judging on, right? Because 1.96 or 1.64, I mean, if it is way beyond 2, I mean, it's more than 2, is usually almost like a reject. Is that okay? Is that clear what we have covered? Because this is covering the one sample test. And after that, we do 2 sample tests, actually the same thing. We will just do the same thing, but the only difference later you will see as we cover afterward is how we construct denominator. That would be the key thing, okay? Denominator and the degree of freedom was a T table we're looking at. Which table we're looking at will be the main thing here. But is there any question before we proceed? Just stop a little bit because I hope you know how to do one-sided for this one, right? That should be no problem. Okay. Is that okay? I mean, in this case, one-sided still reject. Sorry, one-sided you can't reject. You still can't reject because one-sided is 0.7, right? If you happen to be a, okay. Is there any question? If no, then we can, okay, we're happy, we're done with the one-sided one. So much, I think we're on a schedule right now. So it's not, we should be able to finish everything. Okay. So here we have 2 sample tests. Okay. One sample test is very convenient. Okay. And here we have 2 samples. And actually, this is something that we use actually more often than just one sample, right? And one sample maybe the application may be, okay, someone claimed the iPhone can last for 10 hours. You want to check this claim, or someone claimed a certain number is given by application, right? And this used to test the claim directly, okay? And actually, someone asked during the break is, okay, if I reject this or I don't reject this, what do we learn? I mean, hypothesis testing is more like the destructive process. It's trying to see if you can reject or not. Okay, if we reject, it's just reject. We can't say anything more. We just accept the X. I just say the data likely support X1 rather than X0, but X1 is so big that we can't really say which particular X1 we're picking at. Okay, and probably you would go to see, is this sample proportion is good enough, right? If that is the right thing, that might be your new null. Okay, but it's a destructive process. It's trying to see if the null hypothesis is reject or not. Okay, so that is the idea. Okay, we don't establish anything here, but we just try to see if we can, the data is supporting or finding the current evidence of the H null. Okay. Now we have 2 samples. As we said, that actually I claim is going to be more useful. Okay, because 2 samples, actually you are comparing 2 different treatments usually, as we said. Okay, because you can talk about control experiment. Okay, so the main use of this is basically a lot of users is like, you want to see the impact of certain treatment. In terms of business application, you may want to see if some certain, say for marketing, suppose you have 2 different advertising methods, right? You want to see if one is better than others, right? Or you can compare whether online stores are selling more than offline channel, right? You compare 2 things, right? Or in the medical application, you want to see if someone taking the vaccine is likely to get the disease compared to those who don't, right? Or taking the higher doses is better than taking low doses, right? You compare the 2. Are there a difference between the 2? Right? So these are the application. So you can compare 2 groups and see which group is actually doing better. Okay, and that actually hints what we're doing after this one. It's called ANOVA. It's comparing more than 2 groups. Okay, so here I just compare the performance of 2 groups. Okay, and the next topic we talk ANOVA, which compare more than 2 groups. Okay, and they're more general, but here we focus on the case where only comparing 2 things. Okay, that is sometimes we call the pilot program is like this, right? Compare the 2 things, whether they're good or not, right? So that is a very useful things we do. Okay. So here we focus on the case where we don't know the variance. Okay, and that means that we don't know sigma square. Okay, and we don't talk about the case we know because you can see everything will be the same by changing the z. Okay, so that's why to save our life, we just focus on the more general case, right? Because if you know, then the case is actually the same. Okay, I mean even easier. Okay, we focus on the more real case, and as we said, we compare 2 different mean from different group, right? We say, for example, we compare boys and girls, right? Is boys going to perform better than girls? right? Say in terms of academic performance, in terms of social skills, whatever, right? And that you compare two groups, right? And if you look at recent court case actually happening now in US, is talking about whether Asian are discriminated against when in the Harvard admission. Okay, in that case they'll compare between Asian and non-Asian, right? So that is two groups. Okay, actually that's what's going on here. And what here doing is, what happened here is, maybe I just draw a picture, right? So this is a one population. So this is a one sample test. What we are asking is the following. So we have population 1. Okay. You can imagine these are girls. Okay. And there are population 2. Okay. These are all boys. Okay. You may want to compare, I don't know, how much income they're making or how much time they spend on Netflix, so on and so forth, right? What you care is, you have in this group, you have the mean male population 2, right? Population 2. This population mean is male 2. This average for the girl is male 1, okay? And of course they have sigma square 1, okay? And you have the variance also there, okay? And maybe we care about, as I said, the time they watch the movie or whatever. There are many things you want to look at, right? So that is the thing you want to care. But the interest you're looking at is, you care about this guy, male 1 minus male 2. Okay, so this is something we care, right? We want to see if, okay, suppose marketing per department, right? We know men and women may have different favorite type of program for Netflix. Suppose we work on Netflix, right? So maybe women like to watch romantic movie than men, right? And men like to watch violent movie, right? Or scientific movie. I don't know. I mean, I don't watch Netflix very often, but suppose it's the case. I mean, that's my stereotype, but maybe I'm wrong. But anyway, so you want to try to see if is it more, suppose this is the time they spend on watching Netflix, right? So you want to see they're different or not, right? If they're not different, then you probably don't need to skew your strategy towards one or the other, right? If they're same, right, then you probably would produce as much of romantic program as much as scientific program, right? If actually women watch more, then you of course want to produce more love stories, right? So this is the interest we are looking at. And what is important here is, the question is depend on whether this is same as this one. Okay, this is what we call the equality. They have equal variance. Okay, this is case 1 we're looking at. We'll look at it today. Okay, if we have time, we also look at case 2. Okay, case 2 is when they're not equal. When they're not equal. Okay, so this is the first 2 cases we're going to look at. Okay, is that clear? So this is 2 cases we'll look at, whether they're same or they're not same. I think I focus on the, I don't know whether I cover the same first or I know. Anyway, I don't know which one's first, which one's second. Anyway, let me check. I covered the same first. Okay, that's fine. Yes. Okay, this is the first thing. Now the second thing we want to look at is look at another case. Okay, it's what we call a treatment thing. Okay, so here we have 2 distinct group, right? Man and woman. Okay, and and sometimes actually the population 1 and maybe I can use the other one. Okay, so maybe I can use this one. Okay, now the next scenario is we want to look at, there may be some connection between the 2 populations. Okay, the case would be like this girl number 1, actually is a boyfriend, which is boy number 1. Okay. And similarly, this girl number 2, okay, is actually has a boyfriend of boy number 2. Okay. And similarly, we have girl number 3 has a boyfriend is boy number 3. Okay. Which means that each one from population 1 has a pair, one and the only one in the 2. Okay. So in this case, actually what your care about, I don't know, you care about whether, okay, the one you care is how much time the difference of watching time, the difference. Okay. So what I mean is, instead of talking about difference between the average of 2, what you care is what is the notation I use? X1, X11, I think X11. Okay. So she watched with the time X11, and this girl will be looking at is the time they watch is X12, right? And this is X13. May I use the red color? Okay. X13, 11 here. Okay. So this is each one they watch in this way. Okay. And same for the man. Okay. For the man, we also have X21. Okay. And the man also watch Netflix with X22, right? And the boy number 3 will be X23. Okay. So what we're interested is looking at how different they are. Okay. We're interested not just the average of the mean, but we care about X11 minus X21. Okay. We care about the paired observation care about difference. Okay. We care about a couple. Okay. How much time difference. Okay. Because we can pair. Okay. And we try to see if this is 0 or not, right? Because every pair we can construct the difference. Okay. So instead of caring the mean of 2 populations, okay, we care about a pair population. We care about each pair, what's the difference. Okay. And this is exactly what happened in all the scientific discovery, right? Population 1 is the treatment group. Population 2 is the control group. You care about the treatment, is the difference, right, between them, right? Maybe population 2 is those people who have no vaccine. 1 is those who have vaccine, right? And why they're pair is one way is like, okay, they are very similar, so you can pair. Or you can look at things before they take their vaccine and after their vaccine. Right? So that is the idea how you do it, right? Or you can think about yeah, that would be the thing. It's like the pair, the population. That's the case 3 we're covering. Case 3. Okay. So let me repeat what we are doing here, right? So case 1 and case 2 is talking about the 2 populations actually have you cannot collect each observation, right? So look about the difference between the 2 mean. And here we talk about a population of pair. So for each one from 1, you can find another one from 2. Okay. So then you actually care about the difference between the observations. And that actually is what happened, right? Maybe you take something, right? Some medicine, right? Say, suppose look at the hair, right? A lot of people look at the hair, right? And before taking the medicine, hair is like this. Take the medicine, hair very, very long, right? You see this, right? And some people say, okay, you take the medicine before it's very fat, very big tummy. Take the medicine, the tummy is gone, right? A lot of those things, right? Or take the medicine, you have very big Before you have very small bicep, after that you have very big bicep, some and so on and so forth, right? How can you show this is the case, right? You have to take the difference and see the difference is more than 0 or less than 0. Is that clear? So that's what we are doing. And let's see what else, okay? So this is 3 tests, okay? And number 4 actually is so simple. Number 4 is actually a case 4. It's a special case of 1 and 2. Just focus on binary data. Binary data. Okay. If we talk about just 1 and 0, right? Say we don't look at proportion of, say 1 and 2 is men and women, right? Proportion of women watch romantic movie, right? Is it the difference between the proportion of the men who watch romantic movies compared to women, right? Or the same, right? Or you want to check the possibility of a idol, right? Is it more woman like mirror or compared to men, right? I don't know. I mean, that might be, right? So that would be the idea. Okay. So compare proportion. So look at 2 population. Look at proportion. Is like, suppose, is it more woman like cat than men, right? So that is the idea. Okay. So lastly, okay. These are all about mean, okay. And the very last thing is look at with the case 5, so 5 more tests. The last test is talking about whether sigma 1 is actually equal to sigma 2. Okay, is the variance between the 2 populations the same or not? Okay, so this is the test. Actually, is something new. Actually, require F distribution, which we talk about at the very last. But that is comparing the variance, and probably you want to ask why we want to compare variance. Okay, there are many scenarios why you want to compare variance. Is if you compare variance, you can see whether you want to use case 1 or case 2. So that is the reason why you want to use compare variance. And later you will see when we do ANOVA, we also would use F test. Okay, so that is the F test will be very convenient because we compare variance. So that will be useful for the next topic and when we talk about regression. So that's when you compare variance. And other reason why you compare variance is to see, you look at 2 different populations, basically it's reflecting a model. Okay. The idea is you are doing a data analysis, right? So you may have model 1, okay? You have model 2, okay? Model is not the woman or man model. Model is a mathematical model, okay? You try to have a data, try to fit the model in there, right? And to see how the model fit or not, right? You look at what is not explained by the model, right? And you can check the variance of unexplained part, right? That is how well the model is being fit. Okay, so let me read statement here. I have 2 models here, right? And you want to decide which model you want to use. Okay, how do you decide? One you look at what is not explained by the model. What is not explained? Okay, and what's not explained? Okay, say for each observation you can have parts not explained, right? For example, like suppose the model predict the GDP is, okay, suppose this way, right? For example, like this, okay? I must explain. It's like GDP or a stock price, right? Suppose the data tells you 10, okay? If one model tells you 11, one model tells you 12, what's explained? Model A not explained is 1. Model B, the model doesn't explain is 2, right? What's the error is a difference, right? The difference between that, and you can calculate the variance, right, for this kind of error, right? And you want to compare which one lead to bigger error, right? If they're the same level, then you cannot tell which one model is better, right? If one model have bigger error than the other, then you would take the one that is smaller. Okay, that's actually underlying what we do in ANOVA. Okay, ANOVA is trying to make some assumption on the data, build a model. We try to see if the model makes sense. Is try to see if the model actually lead to a smaller variance on the part that is not explained. Okay, the same we will do regression. Okay, regression is not the same idea, because regression is, remember, is try to, right, is trying to see is a, which we will do, right, the scatter plot, right? We are what to do is trying to build a line to explain that, right? What is not explained is like these are the unexplained area, right? If the variance is very large compared to the standard model we are using, then we will say this is not a good model, right? So that will be more clear when we talk about regression. But that's the main idea that we are talking for the two-sided hypothesis testing, right? First, we talk about next class we talk about case 1 and case 2, or for the case 3, okay? And then we'll cover the rest, okay? So probably one or early next week we'll finish this hypothesis testing, okay? So don't worry, we should be able to finish everything on time. Okay, so I will see you on Wednesday. Oh, sorry, Thursday.